So question 5, we have this base source vertex. This is our source vertex. Okay, so this is our source vertex. We will start from the base, and then you can write towns in any order. So rather than town 1, I will be using T1. Okay, so but in exam you will have to use the whole word. Town 1, town 2, town 3. How many times do you have? 6. Town 4, town 5, and town 6. Okay. All right. So from base to base, first we have to check from base. This is marked 1. At one given time, we will only mark one vertex, which is obviously the least. So base, from base to base, it is 0. And rest we don't know. When we don't know, we use infinity. Infinity is endless distance that we have no idea about it. Now we will mark the least. Infinity is something that we don't know. So we will mark what? Base. Whatever that you mark, you should write on the left. All right. Then you see what is attached to base. Town 1, town 2, town 3. So town 1, town 2, and town 3. These are attached. Now there's a formula which says new destination value is equal to minimum of old destination value or marked value plus edge value. This is the formula. We have to see, this is only for those which we have identified that they are connected to the marked vertex. So town 1, town 3, and town 2 are connected to the marked vertex. Now we will take everyone and we will apply this formula. So the old destination value is infinity. So we are not going to take it. Marked value is 0 and edge value from base to town 1 is 4. So old destination unknown, that is unlimited, that is infinity. Marked value is 0. 0 plus 4 is 4. So this will become 4. That is the minimum one. Now town 2. Town 2 is having an edge of 2. So previous old destination is infinity. Marked value is 0. 0 plus 2 is 2. And then we have town 2 is 5. Town 3 is 2. Town 2 is 5 and town 3 is 2. Okay, now town 3 is having an edge of 2 and town 2 is having an edge of 5. Now rest will be copied the way they are. We won't copy the one that we have marked. Now we will see which is the least. Town 3 is the least. So from base, we will go to town 3. Okay, now we will take town 3. Town 3 and we see that how many are attached. From town 3, base is attached since it is marked, so we are not going to take it. So from town 3, town 1 is attached. Town 1 is attached. From town 3, base is attached, so leave it. And then town 5 is attached. Okay, so from town 3 that we have marked here, town 3 that we have marked, base is attached, but since it is already marked, so we are leaving it. Then town 1 that we have marked, then town 5 that we have marked. No other town, no other vertex is attached to town 3. Now, old destination value is 4, marked value is 2, and edge value from town 1 to town 4. So let's see. Old destination value is 4. Minimum of old destination value is 4. Marked value is 2 plus the edge value. Now edge value of what? Town 1 and town 3. The edge value of town 1 and town 3 is 1. So this is either of 4 or 3. Which is minimum? 3. So we will mark it as 3. All right. So this is now 3. We will take now town 5. Old minimum of old destination value is infinity. Marked value is 2. The distance from town 3 to town 5 is 1. Town 3 to town 5 is 1. So 2 plus 1 is equal to 3. All right. Town 5. Okay, so this is 3 as well. Now we copy the rest, leaving the one that is actually marked. Now you see we have got 2 3s, so we can take any of these. So we will take the first one. Now this is marked town 1. Now from town 1 we will see what is attached. Town 3 that is marked, town 4. Base that is already marked, so town 4. So we have taken town 4. Now minimum of old destination value, which is infinity, mark 3 plus the difference between town 1 and town 4, that is town 1 and town 4, that is 7. That has become what? 10. All right, so what is minimum? Infinity out of infinity and 10. 10 is minimum, so we will copy it. 10. Now new destination value is now 10. So we copy the rest, except those which are marked. Now we see which one is the least. 3. We marked town 5. Now from town 5 we see that what are attached? Town 4 is attached from town 5. Town 3 is attached, but it is marked. Town 2 is attached. And town 6 is attached. Now, let's start from town 2. So, minimum of old destination value, 5, marked value, plus the edge value. Edge value of what? T5 and T2. So, T5 and T2's edge value is 3. So 3 plus 3 is equal to 6. So we will keep 5. Now, town 4. Minimum of old destination value, marked value, and the edge value. Edge value means edge value between town 5 and town 4. So edge value between town 5 and town 4 is 6. 6 plus 3 is 9. So we will take this time 9 because 9 is less than 10. Now town 6. Old destination value is infinity. Marked value is 3. And the distance between town 6 and town 5, town 6 and town 5, the edge value is 5. So 5 plus 3 is 8. So what is minimum out of infinity and 8? 8. We marked. Now we copy the rest. There is nothing to copy since this one is marked, this one is marked, this one is marked, this one is marked. Now we are left with these three values. Which one is the least? This one is the least. So we mark it. This is T2. All right. This is now T2. Okay. Now what is connected to T2? Town 2. Base is connect, that is taken, that is marked. Town 6 is connected, so let's take it. Town 5 is connected, it is marked, and that's it. So now let's take 8. Okay, minimum of old destination value, marked value plus the edge difference between town 2 and town 6, that is town 2 and town 6, that is 8. That is 13. So what is minimum, 8 or 13? 8. So we keep 8. We copy the rest and then we take 8. So this time our marked vertex is T6. So what is connected to T6? Town 2 marked already, town 5 marked already. Okay, and then we are left with T4, so we just copy T4 here, 9, and we mark it later. Okay, so that is how. So now these are the value. So town 1 is basically 3. Here we go. Town 2 is 5 whenever it is marked. Town 3 is 2. Town 4 is 9. Town 5 is 3. Town 6 is 8. This is your answer. You have to perform this complete working. After that, you will be able to answer it. So your answer is 352938. If, let's say, not confirmed, but what if they ask you what is the minimum route from base to town 6? In that case, you start moving from town 6 to the point which is different. So this is different. From here, you will take the marked vertex, which is 3, then you move to the point where it is different. From that line, you will take the marked vertex and you will move further. So this is base to, so this is base to town 3, from town 3 to town 5 to 8. Base to town 3 to town 5 and then town 6. That is how it works. So if they ask what is the minimum route from base to town 5, in that case you will start from here. So you will go up whenever there is a changed value, you stop there and see which value is marked. So it means that from town 5 you go to town 3 and then from town 3 to base. So town base to town 3 to town 5. But basically Dijkstra algorithm is asking for the distance from the source vertex to every other. So you won't be asked for any particular one single town shortest distance. But if it is A star, then yes, you will be asked for the shortest distance. Now, explain the use of graphs to aid artificial intelligence. To aid artificial intelligence. Artificial intelligence networks can be represented using graphs. All right. Artificial intelligent networks can be represented using graphs. Now, second point is artificial intelligence graphs has relationships which artificial intelligence networks also exhibit. Graphs provide a way to show relationships between vertices as with AI networks. All right. Graphs can be scanned and analyzed using different kinds of AI algorithms. What are those algorithms? Like A star and Dijkstra. All right. All right. Give two benefits and two drawbacks of packet switching. Now the question is changed all over. Two benefits and two drawbacks of packet switching. Packet switching benefits shared internet path, internet network path, so that all types of packets can use the same path. All right, so this is shared space. Packets are sequenced and encrypted, so there is accuracy and security possible. Okay, drawbacks. Packets can take different routes and may go astray. So delays might happen. This is one of the drawback, that packets are packets. They can go astray, they cannot reach, or they can take different routes. So the packets, because of the loss of packet or longer routes, the delay can happen. Okay. The protocol to deliver packets is very complex and it cannot be used for time-bound real-time data delivery like telephone. Okay. All right. Now the diagram shows a logic circuit. Okay. Complete the truth table for the given logic circuit shown. So what is P? A exclusive or B? Whenever the input is same, the answer will become 0. So P is A exclusive or B. 0, 0, 1, 1, 1, 1, 0, 0. All right. Now Q. Q is A and B. So 0, 0, 0, 0, 0, 0, 1, 1. R is P and C. So P and C, 0, 0, 0, 1, 0, 1, 0, 0. So why is P exclusive or C? P exclusive or C is Y. P exclusive or C is Y. Remember, this is different. Huh? P exclusive or C is Y. So 0, 1, 1, 0, 1, 0, 0, 1. Z is R or Q. So R or Q is 0, 0, 0, 1, 0, 1, 1, 1. So this is your answer. Okay. Now state the name of the logic circuit. All right. How many types of logic circuits that we have studied has two outputs? There is just one, adders, half adder and full adder. Now, if there are two inputs, then it is half adder, but there are three inputs here. So this is full adder. In our syllabus, we have got just one predefined type of circuit with two outputs, and that is adder. If there are two inputs, then it is half adder. If there are three, then it is full adder. Okay, write the Boolean expression for the output Y. Y is P. P is A exclusive or B. Exclusive or C. Okay. Write the Boolean expression for the two outputs X and Z in the truth table as sum of products. Achha, we have to make sum of product. Okay, so Y is actually A exclusive or B exclusive or C. So we have to take just y first. So y has one here, 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 and here. So we will take this, 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 and this. So first is A naught B naught C. Second one is A naught B C naught. Third one is A B naught C naught. Fourth one is A B and C. This is for Y. So we will write it A naught B naught C plus A naught B C naught plus A B naught C naught plus A B C. Now let's take for Z. We have one here, 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 and here. So here we go. A naught B C, A B naught C, A B C naught, A B C. A naught B C plus A B naught C plus A B C naught plus A B C. Now the purpose. So this Y is basically sum and this Z is basically carry. Acha, I tell you one thing, mostly where there is carry, there is this last OR gate. Okay, so on the side where you see OR gate, it is carry. And on the other side, it is sum. So Y is sum and Z is basically carry bit. Sum bit or carry bit or output, whatever you call it. This is full adder, yes. This is full adder. Okay, now state two factors that may affect the performance of a sorting algorithm. Number one, order of data. Order of data. If it is sorted, if it is partially sorted, it is fully unsorted, it is totally haphazard or whatever. Number of data items. Number of data items. Obviously, if we have got thousands of data items, it will take time. Performance will be degraded. If we have less number of items to be sorted. And then algorithm that we are using has efficiency in it. Rather, we write algorithm is efficiently written. Okay. All right. Now, the given algorithm is a simple bubble sort that arranges a set of scores stored in a one-dimensional array into descending order, not greater than, this time we will write less than, and orders the corresponding student names stored in a two-dimensional array in the same order as the scores. All arrays are indexed from 1. Okay, all right. So we match scores and we will shuffle names as well. Okay. So that is why we have got 3 temporary variables to store score and name 1 and name 2. Okay. Write an algorithm using pseudocode that will perform the same task using an insertion sort. All right. So we will check the first one and we will also sort this one.